if I have a hill like this and a car, let's say, at the top of that hill, not moving, what type of energy does that car have at the top of the hill? It's got potential. Not because it's at rest. Be careful there. We don't say it has potential because it doesn't have kinetic. We say it has potential because it has a height. So it does have potential energy at the top of the hill. Now, that potential energy is stored energy. It's the ability to do work. It's the ability to get something moving. Now, that potential energy, as this car rolls down the hill, gets converted to what? Kinetic energy. So at the bottom of the hill, it has kinetic energy. How does the kinetic energy at the bottom of the hill compare to the potential energy at the top of the hill? Do we have more? Do we have less? Like, let's say we had 10 joules of potential at the top of the hill. How much kinetic would we have at the bottom of the hill? 10 joules. 10 joules. If there's no friction or any kind of external forces acting there, then we would have 10 joules. This tells us or illustrates for us the law of conservation of energy. The law of conservation of energy says that the total energy, the total mechanical energy at one place is going to be the same as the total mechanical energy anywhere else. In other words, energy can't be created and it can't be destroyed. It can be transformed from one type to another. It can be converted from potential to kinetic. Or if the car was going up the hill, it can be converted from kinetic at the bottom of the hill to potential at the top of the hill. But you can't destroy it and you can't create it. The best you can do is transform it from one type to another. Josh, question? Energy cannot be created or destroyed, but it can be transformed from one type to another. Potential to kinetic, or from kinetic to potential. Basically, it amounts to this. If something speeds up, it's potential to kinetic. If something slows down, it's kinetic to potential. Now, it does sometimes appear as if energy is being created. We start off with 10 joules of potential energy at the top of a hill. We end up with 12 at the bottom of the hill. Energy's been created, right? Well, no. It means that energy's been added to the system from some other source, like wind, or somebody's pushed it. The total amount of energy, if we account for everything, including what was added to the system, still remains the same. Now, on a similar note, it appears as if energy is sometimes destroyed. We start off with 10 joules of potential energy at the top of the hill. We end up with 8 joules of kinetic energy at the bottom of the hill. 2 joules was destroyed, right? Well, no. 2 joules because of friction or because of air resistance or something else, 2 joules was taken away from this. Not destroyed, but taken away, converted to some other unusable form, usually heat. So even if it appears as if energy is created or destroyed, it isn't. It just sometimes is converted to or from a source that is a little bit more difficult to account for. The problems that we will do involving the law of conservation of mechanical energy will all assume that we don't have external forces, that we don't have air resistance or friction or anything else that's taking away energy from the system or adding energy to the system. It's possible to solve these problems even if there is friction. It's just more difficult because we have to account for the heat that's dissipated as a result of that friction. So how exactly do we go about solving a problem involving conservation of energy now? Well, because the total energy remains the same, we can say for every single one of these questions, EI, the initial energy, wherever we define the initial point of the question to be, EI will be equal to EF, the total energy at the end of the problem. Now, there's 2 kinds of energy that we've dealt with and that we know how to deal with: gravitational potential and kinetic energy. So what we're going to say in the initial place, where the initial energy exists, we're going to say not always There's not always potential energy, there's not always kinetic energy, but you have the possibility of having potential and kinetic energy. And at the end of the problem, at the final part of the problem, you also have the potential or the possibility of having final potential and final kinetic energy. What you've got to do at this point is decide, okay, at the beginning of the problem, do I have a height? If I do, then I've got potential. If I don't, then you would cross that term off. Is the object moving? If the answer is yes, then you've got kinetic. If it's not, then you would cross that term off. At the end of the problem, do I have a height? If the answer is yes, okay, put that in. If it's not, if there's no height, then cross that term off. Is it moving? If it's moving, then you would put in the speed. If not, then you would just cross that term off. Now, realistically, there's a lot of problems that we can solve using this method, using conservation of energy. Okay, but usually they involve problems where there is a change in height. The exact path of the change in height is irrelevant. The object can go up into the air like this. It can go down like this. It can go over a hill like this. It can go down a hill like this. It can go any kind of a roller coaster type thing like this. Doesn't matter what the path is. As long as there's a change in height, it's usually a practical thing to use the law of conservation of mechanical energy. Let's take a look at an example. It says a ball was thrown, a 500-gram ball was thrown downward at a speed of 5 meters per second from a height of 35.0 meters. What's the speed at which the ball hits the ground? How fast is it moving when it hits the ground? Now notice that this ball was being thrown straight down like this. That's fine. If the ball was taking a path on a track like this, we'd get the same answer. If the ball was going down like this, around a little loop like this, and over a hill like this, as long as it started at the same height and ended at the same height, the answer for this question would be the same. So you don't have to know what path it's taking in order to use conservation of energy. You just need to know its initial conditions. Is it moving? Does it have a height? And its final conditions. Is it moving? Does it have a height? So regardless of this path here, we're going to set this up by saying EI equals EF. The energy of this ball at the beginning of this problem will be equal to the energy of this ball at the end of the problem. Now, what type of energy do you have at the beginning? Remember, we can have up to two kinds, gravitational potential and kinetic energy. We have to decide whether we have a height at the beginning of the problem. Do we have a height? Yes, we do. Therefore, we have gravitational potential energy. Let's include MGH. If there was no height, then we would just cross off the MGH or not even put it in the first place. Is the ball moving at the beginning of this problem? Yes, it's moving at 5 meters per second. Do we have kinetic energy? If it's got a height, it's got potential. If it's moving, we've got kinetic. So we're going to sub in 1/2 mv squared for that. Now, that equals the final energy. Ask yourself the same two questions at the end of this problem. Does it have a height at the end of this problem? No. It's reached the ground. Relative to the ground, it has no height. Therefore, we will cross off the MGH final term or just not include it in the first place. Is it moving at the end of this problem? What's the speed of the ball when it hits the ground? Is it moving? What's the speed as it hits the ground? Yeah, it's moving. Otherwise, it wouldn't be a speed, right? So we're going to say that it does have kinetic energy at the end of this problem. What's my conversion that takes place here? Kinetic to potential or potential to kinetic? The total energy remains the same. Potential energy decreases, kinetic energy increases. Therefore, we have a conversion of potential to kinetic here. Anybody see a shortcut? Yeah, Sean?
Mass cancels out.
Yeah, mass cancels out because it's in every term. See that? As long as it's in every term, it doesn't matter how many terms we have. As long as it's in every term, then we can say it cancels out. So it's a 500-gram ball, but what we're really saying here is that it doesn't really matter if it's a 500-gram ball. If it was an 800-gram ball, it would be moving at the same speed when it hit the bottom as if it was a 500-gram ball. And that should make sense to us, right? We know that every object, independent of mass, accelerates at 9.81 meters per second squared. So we know that it doesn't, deep down, we know that it doesn't matter how heavy it is. Let's sub in our numbers here. Remember that energy is a scalar, so we're just going to sub in positive values here. 9.81 times the initial height of 35 meters plus 1/2 of VI, which is 5.00 squared. This is the situation where I would suggest you do not rearrange first. Sub your numbers in, then rearrange. Okay, let's get the left-hand side here. Simplify that a little bit. Let's say 9.81 times 35. Let's press equals. So let's add to that. Let's add to that brackets 0.5 times 5 squared and the brackets. On the left-hand side, I get 355.85. How do you take the half over? You get two options here, really, right? How do you take a half over to the other side? You could divide by half, or you could multiply by 2. Either way, I'm going to say 355.85 divided by a half or divided by 0.5. And then let's square root that. We end up getting 26.67. So at the end of this problem, after the ball has gone down 35.0 meters, it's moving at 26.4 meters per second. Whether it goes straight down, as it is in this problem, or whether it took a path like this, as long as it goes from the same starting point and the same ending point, the path that it took is irrelevant. Why does it not matter? Listen carefully to what I'm about to say. Why does it not matter which direction this ball went in order to find the final speed? It does? Well, it could change direction, right? Why does it not matter which direction the ball travels in order to get the final speed? Because speed and energy are scalars, and directions are relevant for scalars, right? So straight down, take that funny roller coaster type path, doesn't make any difference. The answer is going to be the same. Now, the velocity would be different, right? The velocity here would be straight down, a certain value straight down. Here the velocity would be at some other direction, right? But that's because velocity is a vector. Speed is a scalar. We're just looking for how fast it's moving, and we're looking for the speed. All right, I'd like you to take a look at the next worksheet, the last one in that little booklet that I gave you earlier on. Energy worksheet number 5, titled Conservation of Energy. And I'd like you to take a look, please, at the first 5 questions on that worksheet. Worksheet number 5, questions 1 to 5, please.